Hello everybody, and welcome to the forward plotting room aboard USS New Jersey. She's currently in dry dock, and some of you have seen the video I did on fire control systems generally, but we're now going to look at fire control systems in particular, the one on USS New Jersey, and the one that's near enough with a few minor differences common to all US fast battleships and other major warships of the Second World War. Now, to do that, we have with us a man who has probably forgotten more about US fire control than most of the rest of us will ever know, Dr. John Scholes. So if you'd like to give us a little bit more information about yourself, please go ahead.
Hi, I am Dr. John Scholes. Many people think I served in the Navy, but unfortunately I never really had the privilege. However, I have had the privilege of being a supporter and volunteer on a number of historic naval ships, particularly USS Massachusetts and USS Salem, for over 30 years. I've actually been studying Navy ships and naval history since I was about 8 or 9 years old. At that time, I lived in Hampton, Virginia, which is directly across Hampton Roads from the main Atlantic Fleet operating base in Norfolk, Virginia. So while other kids did cowboys and Indians and fire engines, I drew battleships and cruisers and aircraft carriers and destroyers. My special interest in terms of ships is in the big gun ships, battleships, and cruisers, and particularly the aspect of naval gunnery, and that includes both the armament itself and the systems that control it. I am what is called a battleship nut. I've had the privilege of giving firepower tours on board the USS Massachusetts, as well as a number of other tours on the Salem and the Massachusetts, and have been able to work with a man who actually fired 16-inch guns, gunner's mate Tom Lowney, who was on the USS Wisconsin. I've also been very helped in my studies by Chris Nardi, the curator and now director of the USS Massachusetts and Battleship Cove, for giving me ordnance publications on the Mark 38 Director and associated fire control equipment, as well as the gunnery doctrine of the USS Massachusetts in 1945, which explains how they actually used the guns. Now, the 16-inch guns, of course, are the reason that the fast battleships of World War II U.S. Navy were built. Everything else on the ship is there to support the guns. The armor is there to protect them from the effects of enemy fire. The engines are to move those guns to where they are supposed to be, to do what they need to do. The crews are there to operate and maintain them, and the support facilities are to feed and supply those crew members, as well as all the components that the ship needs to operate. While they're immensely powerful and effective weapons, they can only be so if they're able to hit what they're supposed to hit. They need to do this in order to do their job, and the job of getting them to hit what they need to hit is the job of the fire control system. Now, when the Massachusetts and the other fast battleships and the New Jersey were built, their primary targets were anticipated to be enemy battleships and other large vessels at sea. However, the problem of hitting a moving ship, however large it is, or other large vessel at sea, from another moving ship, especially at a great distance, as much as 21 miles for the 16-inch 45 caliber gun, as much as 24 miles for the 16-inch 50 caliber gun, is anything but easy and straightforward. It's a mathematical and technical problem of mind-boggling complexity, involving over 24 variables. Most of those variables are continuously changing. Usually they're changing at variable rates, and the rates at which the variables are changing are also varying. And most of these variables also affect other variables and cause a difference in the rate at which they change as well. Even though a battleship is a relatively stable platform for a ship, in a seaway, particularly when the seas are rough, the ship is rolling, pitching, and yawing continuously. It's also moving along its intended course up to 27 knots for the North Carolina, South Dakota class, up to 33 knots for the Iowa class. To give you an idea of how difficult it is to hit a moving target from another moving platform, imagine this analogy. You're in a car and you're driving along a rough, bumpy, twisting, winding country road doing 30 miles an hour, which is about 27 knots. Now imagine another car on another similar country road, roughly parallel to the road you're on, which is also going about 30 miles an hour, and that road is some distance from you. For the simplest problem, we'll make that car essentially directly across from you. At a 90-degree angle, you have a pistol in your car, and you're the good guy, and the other car is full of bad guys. So you want to stick your pistol out the window of the car and see if you could hit the other car. Now, if that distance was very, very short, say about 20 feet, you might have a chance of hitting it, even though your pistol's going to be doing this. You might get lucky. However, if you make that distance 10 times longer at 200 feet, or something just short of 70 yards, it becomes extremely difficult. Now make it 100 times longer at 2,000 feet, which is a nautical mile, and it becomes essentially impossible. You could never do it, even if your pistol could shoot that far. But a battleship, you say, well, that's a much bigger target than a car. A car is, say, about 15 feet long, and to take the shortest of the fast battleships, the Massachusetts, it's about 45 times longer than that. So we could multiply that 20 feet by 45 and get 900 feet or 300 yards. At 300 yards, you might be able to hit something as big as a battleship, again with your pistol out the window. But if you raise that distance to 100 times more, then 200 feet becomes 9,000 feet or 3,000 yards. And you're already well beyond the distance where your pistol could shoot, but you're approximately at the distance at which a single gun laid by a single gun layer through a telescopic sight using the continuous aim fire control methods of Admiral Scott and in the Royal Navy and Admiral Sims in the US Navy could actually have a fair chance of hitting the target. And that's about the maximum range you do it. Now multiply that by 10 again. And now you're out to 90,000 feet or 30,000 yards or 15 nautical miles or about 17 land miles, at which hitting with an individual gun laid by an individual layer is essentially impossible. Yet, this is the distance at which the modern fast battleships were expected to be able to hit a moving enemy battleship target. And the scenario I have described to you is actually the easiest possible scenario because the rates of change of range, and bearing are very, very small, essentially almost zero. So that's the easiest. Now imagine that you turn the cars around in direction. And one car is going 30 miles an hour in one direction and 30 in the other. So the relative speeds of the cars is now 60 miles an hour, which is about 52 knots. Imagine what it would be like with your pistol. Yet, again, the fast battleships were designed to be able to hit other ships at a great distance, even in that kind of scenario with a very rapidly changing range rate and bearing rate. And we'll give you some examples at the end of how this actually was accomplished during World War II by U.S. fast battleship. Now, all of this was achieved by the Mark 38 gunfire control system with the Mark 38 gun director. Most people, when they think of the Mark 38 gun director, they think of the structure with the rangefinder up at the top of spot 1 and at the top of spot 2, the after fire control. But that's really only one component of the fire control system. That system includes that director, but also the other included components, including the Mark 8 range keeper, essentially a mechanical analog computer, the Mark 41, or in the case of South Dakota class, Mark 43 stable vertical. It also entails the development of electromechanical precision motor controllers, amplidynes and receiver regulators to be able to move structures, including guns and turrets, and also directors under precision remote control from the computer. It relies on reliable, accurate electrical transmission of data so that you don't have to call down, for example, the bearing of the target through a voice tube, have somebody hear it, and then try to crank it in to a computer and maybe mishear it, or the delay in time that it takes to get it in there can cause errors in the fire control system. And then later in World War II, ever more advanced radars, including the most advanced, the Mark 13 fire control radar, and the first precision fire control radar, which was accurate in both range and bearing, the Mark 8, and its modification, the Mod 3, which was an improvement. The system also relies on the search radars to pick up the target initially and to provide an initial course and speed. And once radars were able to do this, that was a big help to the fire control system in order to get an accurate initial solution so that even your first salvo might well be on target, even at long range. And together, this fire control system achieved what was probably the best solution to the surface main battery fire control problem that was sought by many other nations, but probably the U.S. achieved the best solution during World War II and the post-war years. This was a mathematical and engineering accomplishment of mathematical geniuses and engineers, and it still causes amazement by people who study the history of computing and design modern digital electronic computers. Now, the Mark 38 director and fire control system has 4 main components, and each one of those is primarily concerned with one part of the fire control problem and solution, but all of them are interconnected. The Mark 38 Director, that's the visible structure again at the top of the forward or spot 1 tower, and after or spot 2, and after fire control towers, is the director proper and is primarily concerned with establishing the range and bearing and following them, the range and bearing of the target and following them to track the target. This provides data input to the system, and also by means of a feedback control loop, it provides correction to the computer output solution, resulting in an accuracy that was probably achieved by no other system of its era. We'll see the director itself a little later in this video. Now, the heart, or the brain of the fire control system, is located in the main battery plotting rooms. On the Iowa class, there are 2, a forward one and after one, each one containing all the necessary components to do the calculation, and also, as we'll see a little bit later, the stabilization. On the South Dakota and North Carolina classes, there is only one main battery plotting room, and it contains 2 Mark 8 range keepers or computers and their associated stable verticals. This range keeper is located, of course, in the main battery plotting room, which is protected by the ship's main armor, the most protected part of the ship. It contains the predictor component of the system to calculate the course, speed, and position of the target at the present time, but also at both the present time and at any future time on a continuous basis. And it takes this information about the target position and applies all the necessary ballistic calculations to aim the guns at the proper point where the target will be when the shells arrive in the future. The predictor function is performed by the Mark 8 range keeper, often called a computer, built by the Ford Instrument Company. And no, that's not Henry Ford, the automobile manufacturer. It's Hannibal Ford, a mathematical and engineering genius. Unlike modern digital computers, this is a mechanical and electromechanical analog computer. It uses shafts, gears, cams, differentials, and electric motors to solve only one mathematical problem. Although, as we've seen, this is an incredibly complex mathematical problem. Each model or mod of the Mark 8 computer was designed only for not only for one gun, but also only for one ship or ship class if every ship in that ship class were identical. To make its calculations accurate enough to be useful at great ranges, its components need to be manufactured to incredibly tight tolerances, down to less than 1/10,000th of an inch. And in fact, some of the specifications require that the tolerances be at 70 degrees Fahrenheit because metal expands and contracts with temperature. When the Mark 8 range keeper was designed in the late 1930s, it was the most powerful computer in the world. But as precise as it was also incredibly rugged. It's a box that weighs about 3,000 pounds, and it was rugged enough to withstand the shock of 16-inch gunfire, including full 9-gun salvos, which shake the ship up considerably when the guns are fired. When the Iowa class was reactivated in the 1980s, the Mark 8 computer was retained because at that time digital electronic computers could not withstand the shock of the 16-inch guns firing. The Mark 8, which has a different mod for each ship, contains most of the controlling, computing, and transmitting mechanisms of the fire control system. Despite the name, it's more than just a range keeper. It keeps and predicts future range continuously, but also it's a bearing keeper, keeping and predicting target bearing at present time and in the future. It's a deck tilt computer, meaning it senses the tilt of the deck and the tilt of the turrets, which affects the fire control solution. And it also is a trunnion tilt collector, which again, when the guns are elevated, the turret turns like this. It affects the accuracy of the fire control system. It also runs a graphic plotter, and it computes, indicates, and transmits electrically information to point the guns at the target, set the sights, and to train and elevate the guns continuously, and to compute and signal the time of flight of the shells. Its outputs include corrections for drift. These are spinning projectiles, and for example, like a curveball, that spin will cause a clockwise rotating projectile to drift to the right. It corrects for variations in initial velocity, depending on the wear of the guns and the type of powder charge chosen and the type of shell chosen. It corrects for the movement of our own ship and the movement of the target, analyzing both separately and then combining them to get the range and bearing to the target from our own ship. It corrects from trunnion trip, from a horizontal plane, and director tilt also, because it also can stabilize the director, which is necessary to get accurate bearings and ranges on a distant target. The graphic plotter also plots present range, advanced range, and sight deflection. Electrical inputs, or data into the Mark 8 rangekeeper, include our own ship's course, that's provided by gyro compass, our own ship's speed, that's from a pedometer log, or at very slow speeds can be put in by hand by a conversion chart. Director train in automatic for automatic operation, which we'll explain in a little bit. Director train indicated for local operation. Level, which can be either continuous or selected. Cross level, which can also be either continuously provided or selected at a particular value. And then there are also mechanical inputs of data, and those are continuous level and cross level, and selected level and cross level from the stable vertical. Hand inputs that are cranked in manually for data to the Mark 8 include movement of the target, that is course and speed initially of the target, wind, spots, that is corrections provided by a fire control officer, usually by a person actually standing at the computer called the spot coordinator. Generated range, generated bearing, initial velocity of the projectile, the powder charge being used, whether it is the service charge, a reduced charge, or in case of the Iowa-class battleships, there's a special charge to duplicate the ballistics of the 16-inch 45 caliber gun. Selected train, if used. In other words, you can select a particular train angle at which the guns will fire. This is frankly rarely used. And you can also input by hand any of the inputs that are normally received electrically in case the electrical transmission fails. These would include the range, battle order, control order, plot ready signal, transmitters, sight deflection, and sight angle. The Mark 8 outputs its information by synchro generators, which are electrical devices to transmit electrically numerical values, which then are reproduced at the receiving end, either as an indication on a dial or run through a receiver regulator to actually move physically the component that is supposed to be moved to those values. For example, to elevate a gun to the correct value, to train a director to the right bearing. And these include the gun train order in automatic mode, and we'll explain that in a minute, the gun train order in indicating mode, and you can also have a gun train order in information mode, basically just to tell the gun turret, this is where we're planning to train the gun. There's also a gun elevation order in the automatic mode, and in the indicating mode there is no information mode for elevation. Sight deflection and sight angle. This is of necessary values to initially be set by the sight setter in the turret. Generated director train, that's generated by the computer. Bearing correction, which basically means the generated change in the director train, or essentially the rate of change of the director train. Deflection, that is the bearing to the target, the amount the guns must be offset in order to lead the target or trail the target if your ship is speeding past it in the other direction. The range, both present range and advanced range. This is there for information and also so that the guns can be set to the correct elevation and train. And a parallax range function, because all of its calculations are based on a single central point on the ship, and that is the center of the periscope director, the Mark 40 director, that's in the big cylindrical conning tower. All of the distances, both horizontally and vertically, of the gun turrets and the directors must be known from that reference point and corrected for parallax based on range to the target. For example, if the range were very close, there would be a big angle between where the turret is pointing and where that reference point is pointing, and that would have to be corrected for. At a very long range, that's a very, very small angle. That has to be allowed for. Now, the type of computer that we're dealing with, and fire control system we're dealing with, is termed a synthetic system. There are two basic types that were developed for advanced fire control systems beginning in the days just before World War I. The first type that was developed is called an analytical system. And basically what that does is it makes measurements of the line of sight to the target from your ship to the enemy ship. There's a device where you can put in your estimate of the target ship's course and speed, your own ship's course and speed, and by lining up the line of sight, it will show you the change in position of the target with time. In other words, it will give you a rate. This can be split into two vector components. A range component, sometimes called rate along, which would, for example, be the range is closing at 200 yards a minute. That is, you know the target is coming 200 yards closer to you every minute that passes. And then you can also have what's called a rate across, which could be a speed, but that can be converted into a bearing range. So, for example, you could have a change of bearing of 2 degrees per minute. Based on this, you can plot out how the enemy target ship is moving compared to your ship as a reference point. And if you do that, and your ship does not change course, and the enemy ship does not change course, then you end up with a straight line plot. Mostly, this was plotted in range, because that was the most difficult factor to try to compute. And you could tell the rate at which the range was changing by, on a range time plot, looking at the slope of the curve. If the slope went in one direction, the target was moving away from you at a certain given rate. If it went in the other direction, it was closing on you at a certain given rate. You could figure out what that rate is, and by projecting ahead your line of plots that you had made, and you did this actually graphically in many cases. Most of the systems use a graphic system one way or the other. You could then project ahead. Oh, 1 minute in the future, that line is going to intersect this point at this range and this bearing. And then you could set your guns in advance to that and then fire at that exact moment. This is the type of system that was mostly used in World War I. It was effective only in the situation that we talked about with the two cars going along the roads roughly parallel to each other, roughly 90-degree angle, roughly broadside. It did have a corrector mechanism for the roll of the ship. Usually these systems did not have a cross-level mechanism. So the guns really needed to be corrected, be pointed on the broadside so they could be corrected in level, because that was the only correction you had. And if you look at your engagements between battleships and battle cruisers in World War I, almost all of them follow this kind of model. The two lines of ships run on roughly parallel courses with maybe slight convergence or divergence, and roughly parallel to each other, and the ships fire at roughly 90-degree angles across. The synthetic system has many advantages over it. What do we mean by a synthetic system? Well, a synthetic system takes the initial range and bearing and estimated course and speed of the target and calculates what the advance range, that is the range in the future, will be, and the bearing in the future will be, based on the rate of change of rate and bearing as tracked by the director. So in this case, if your ship changed courses, this rate of change of rate will change, the rate of bearing will change. However, the computer will detect this and correct the solution for those changes, and it does this on a continuous basis. This allows you to maneuver. It also allows you to deal with much more rapid rates of change. For example, this system, a synthetic system, can deal with two ships on opposing courses moving at very high relative rates to to each other. Now, almost every synthetic system that was designed has some sort of feedback mechanism to check to see whether this virtual advance range and position of the target in range and bearing is actually accurate. Part of that, of course, can be firing the guns and seeing where the salvos land, and that's one mechanism that was definitely used. But in the case of the Mark 8, there's an additional feedback loop built into the system. The director not only aims the guns at the target, but it also has the director follow the target and track the target. Initially, the director has to track the target with the hand wheels of the pointer and the trainer particularly, and he puts his crosshairs on the target and continuously tracks it, and he has a track. When the computer has a solution based on that track, he can be informed and he will throw a switch and turn it into automatic. At that point, the computer now drives the director through the synchros and the amplitudes and moves the director with no hand input at all. The trainer then watches his crosshairs if he's doing it optically, or fixes the target on a radar scope right in the middle of the scope. We'll show you one of the scopes that he does this on, and follows. If the computer's solution is correct, the crosshairs will stay right on the target optically, or the radar position will follow right where he puts it, and it won't drift. If it starts to drift, he can then take his hand wheels and move them so the crosshairs move back onto the target. This will send an electrical signal down to the computer. The computer will then use this to correct its solution. He can then observe, and now the crosshairs will stay with the target. This gives a big improvement in accuracy and allows you to have a realistic chance of having a straddle and the potential for a hit, even on the very first salvo. Now, by triangulation, the computer takes the predicted position and therefore range, bearing, course, and speed of the target and gives the future advance, range, and bearing of the target, and it gives this both to the director and to the guns. This feedback loop corrects the predicted position and therefore range, bearing, course, and speed of the target, and therefore the future advance, range, and bearing of the target. So the Mark 8 Rangekeeper and Mark 38 Director continuously computes and corrects where the target is and will be, and the place that the guns have to be aimed to hit the target, corrected for factors such as the parallax of each turret, corrected for range. But now we have to correct for the moving of the ship, which we remember is rolling, pitching, and yawing, especially if the sea is rough. And therefore, the train and elevation to point the guns at the correct place is constantly changing due to the motion of our own ship. The correcting component of the system that corrects the solution continuously for own ship motion is the stable vertical. In the South Dakota class, such as the USS Massachusetts, this is a Mark 43 stable vertical made by General Electric. And in the North Carolinas and the Iowas, it's a Mark 41 stable vertical, which is made by ARMA. Also, all of the cruisers of World War II used the Mark 41 rather than the Mark 43. The reason that they made two different types is to have two suppliers in case one of the stable verticals they were developing was not satisfactory. Both of the ones that they did develop operate similarly, and both of them apparently produced similar and very successful results. Now, the purpose of this stable vertical is to designate and maintain true vertical in order to determine angles of level and cross level to correct the motion of the firing ship. It's also there to fire the battery automatically at the proper point and interval and level and cross level. And this would be either selected or it could be continuously done, provided the level and cross level were within certain limitations, usually 15 to 20 degrees of roll and about 5 degrees of pitch. So this provides a means of firing and level and cross level continuously. What are the inputs to the stable vertical? Well, if you do select a particular level or cross level, let's say the ship is moving too fast and you want to, say, fire the guns only at the point of the roll where the ship is directly vertical, 0 degrees, you can do that, and you can put that input in by hand into the stable vertical. Stable vertical needs to know the own ship's course from the gyro compass in order to orient its level and course level, and it also needs to know the target bearing and line of fire to orient its level and cross level. It gets this from the director and from the Mark 8 range keeper. This determines the line of sight. Outputs are continuous level and cross level, and this comes out mechanically, fed back into the Mark 8 range keeper, correcting its already generated output solution in train and elevation of the guns for the movement of the ship, so that they are continuously locked on the target and they continuously move to correct for the motion of the ship. Or if a selected level or cross level is selected, the output of the stable vertical is done electrically. Now, what is a stable vertical? What kind of a machine is it? It's an electrically driven gyroscope oriented vertically or horizontally or both within a liquid mercury damping pool. And this is to precess the gyro back continuously into the vertical position. The gyro moves within a frame with electrical pickups, electromagnetic pickups, that produce current when the gyro moves from its stable 0 position in some direction or another, either in level or cross level. This magnetic field generates an electrical system which is transmitted to mechanical outputs of the stable vertical by gears, differentials, etc. And it also generates a voltage which can be amplified to drive motors. For example, that's how the director can get level and cross level from the stable vertical if it doesn't generate those values optically by itself. So this stable vertical continuously knows, if you will, what level and cross level is without being able to see a horizon the way you have to do it optically, and automatically corrects the computer and continuously then corrects the output of that computer to elevate and train the guns. Now, one feature of all American warships of the World War II era, but particularly the big gun ships, is redundancy. In order to have redundancy, all of the United States Navy fast battleships have 2 Mark 38 directors, Spot 1, which is forward on the main fire control tower, and Spot 2 on the aft fire control tower. 2 Mark 8 range keepers, 2 Mark 41 or 43 stable verticals, as well as a third less capable Mark 40 director and Mark 3 computer in the South Dakotas and North Carolinas in the upper level of the conning tower. The secondary battery Mark 37 directors can be linked to the 16-inch guns in an emergency. Any combination of these can be linked together to control the 16-inch guns. In addition, there are multiple modes of operation to control the 16-inch guns, including automatic, indicating, and local, that is manual, control of turrets and director, period. The gunfire control system can be set up, that is prepared to select linked specific directors, such as spot 1, spot 2, spot 3, or secondary, range keepers, that is computers, 1, 2, or 3. In the case of the South Dakotas and North Carolinas, in the control station at the top level of the conning tower, stable verticals, either 1 or 2, and linked to any combination of turrets, all 3, 2 forward, 1 aft, or 1 single turret, each individually, or any kind of combination. Once the components are selected, they can be operated in multiple types of fire. Salvo, which is firing all the available guns of the main battery at a single target. Partial salvo, which is firing usually 1 or 2 turrets at the target. Slow fire, when the guns are fired, the shells are allowed to splash around the target. They're observed, and then a spot correction is added if they're off target before the next salvo is fired. Rapid fire, which once the correct range and bearing has been determined and the guns are on target, basically fires the turrets as soon as 1 turret or 2 turrets, depending on how you select, are ready to go. You don't have to wait for all 3 in case 1 is behind. Or continuous fire. In this case, all the guns fire as soon as they are loaded, and the ready switch is flipped by the gun captain in the turret to show that the gun is ready. It automatically just elevates the firing position. As soon as it gets to the correct elevation, it fires in the automatic mode. There are also multiple types of control. The main type of control is through the range keeper, that is the computer, and instruments in plot. The fire control circuits are through the fire control switchboard. There is also an auxiliary mode, a local mode. These can be fired directly, that is, if the target is visible to the director, indirectly, using offsets to a target that is not visible to the director, in automatic mode, in which case the range keeper drives both the director and the turrets to keep them continuously on targets, and the guns may be fired as soon as they are loaded and ready and they elevate to the correct elevation. Turrets always training to keep them on target. Interestingly enough, when the guns are fired, the automatic mode also lowers the guns to their 5-degree loading angle automatically, and when the ready switch is switched to ready, when the gun captain steps off his platform, throws the switch, the guns just automatically go back to the correct elevation. They can also be fired in indicating mode. That is by following the pointer. In that case, in the sight stations on either side of the 16-inch gun turrets, the pointer and trainer follow the directions of the follow the pointer indicating system, match up dials, and that way they keep the guns at the correct train and elevation. This is a continuous process. They are continually using their training wheels. And in speaking to Tom Lonnie, the gun captain from the Wisconsin, who actually did this, it's a very tiring process. But a good crew can get very, very good results with follow-the-pointer system. The guns can also be fired in multiple ways. They can be fired by the pointer in the director. They can be fired by a master key, and that can be located in multiple places. Most commonly, when they're in automatic mode, the firing key is on the stable vertical. The guns can also be in continuous aim. This is what happens in the automatic mode or in the indicating mode when the pointers are being followed continuously. They can also be fired at select level during the roll and select cross level if the cross level is more significant than the level in terms of the amount of ship motion. There's also a special mode that the leveler and cross leveler can use during a severe ship motion called intermittent cranking, where they, instead of trying to keep the hand wheels turning continuously to keep up with very severe ship motions, they follow as best they can the motion. And then if the guns are going to be fired at a select level position, just before they get there, they will move their pointers ahead of the motion of the ship to get to the data, and that helps the guns catch up to the director, do it by copying basically the same motion. Rarely they can be fired by also a select train. In other words, you can select a particular degree of training for all the turrets and fire when that train comes on as the turrets turn. That's not used very much. They can also be fired by the pointer telescope in the sight stations in each turret. Again, that's not commonly used. All of this setup on the final components in the plotting room, main battery, and fire control is done through the main battery fire control switchboard. Now, in the gunnery doctrine of the Massachusetts, there are a number of standard setups that are used if possible. For the Massachusetts, the preferred setup in daylight and good visibility, that is, the horizon is clearly visible, would be setup number 1. This would be director fire collective, meaning all guns in the main battery are controlled by the main battery Mark 38 director, usually spot 1. They would be training, leveling, and cross leveling and firing circuits, that is the master key that fires gun, would also be in director 1. So they would be using optical level and cross level because it can be just as good, if not better, than the automatic stable vertical if the horizon is clearly visible enough and you have good enough trained personnel. The Mark 8 rangekeeper, normally number 1 would be used. That's supposedly the best one, and that's linked, of course, to the stable vertical number 1 that goes with that rangekeeper. Now, in terms of night and reduced visibility, they would use setup number 5. Again, this would be director fire collective, meaning all guns of the main battery were firing together. Director 1, spot 1 would be training. The rangekeeper number 1 and stable vertical number 1 would be leveling, cross leveling, and the firing circuits would be going through the stable vertical. and the master key would be in plot at the stable vertical as well. For the Massachusetts, in this gunnery doctrine, there are approximately 30 standard setups, but there's a paragraph at the end saying that there's a potential huge number of non-standard setups that are possible in an emergency. All of these are set up through the massive bank of switches in the fire control switchboard, and there are people who operate who know exactly how to set those switches to get the setup. The final component of the fire control system is translating the electrical output of the system, the director, the range keeper or computer, stable vertical, and the setup in the fire control switchboard to the actual movement of the guns in elevation and the turret in train to point the guns to hit the target. Normally the guns are moved continuously and continuously point at the target by one of two methods. In the automatic fire mode, the computer-generated gun orders for train and elevation are sent through amplidynes, that is amplifiers, to receiver regulator units that electrically control electro-hydraulic motors with feedback control to keep the guns continuously synchronized with the gun orders from the range keeper or computer. Guns may be fired at any time because they're kept continuously on target. This increases the potential rate of fire. This capability for large guns such as battleships or big cruiser guns was exclusive to the United States Navy in World War II. If the automatic mode was not possible, for example, the receiver regulators were not yet fitted in the USS Massachusetts in Operation Torch at Casablanca, the indicator fire was used. In the indicator, electrical signals from the range keeper for gun orders, that is train and elevation, move indicators in the trainers and pointer stations in the turrets who match the indicators with their hand wheel controls continuously. This is the follow the pointer system. Moving the guns, again, occurs through electro-hydraulic motors continuously on target. So as long as the pointers are kept matched, the guns are continuously on target. This method relies on trainer and pointer and their training to keep the pointers matched for accuracy. In director-generated train, the director generates train orders to the directors to keep the director trained on target. This also can be in automatic or indicating or follow the pointer mode. The range keeper also sends a sight correction for parallax to the sight setters in each turret. Once the initial value is set by matching pointers, the system may be switched over to automatic or indicating, that is follow the pointer, and continuous parallax correction for range is provided to the sights and to the turret. If the motions are too great for automatic or indicating mode, and that usually means more than 15 degrees of roll per second or more than 5 degrees a second pitch, a selected point in the roll, that is selected level or pitch, selected cross level, can be used. And this can be chosen either automatically on the stable vertical or manually on the stable vertical. And the stable verticals have hand cranks so that they can actually follow the pointer of the stable vertical to maintain level and cross level. Well, now that you've heard this incredibly complicated system, if it sounds too complicated to work, I think the best indication is actually how did it work when it was used in actual service. And interestingly enough, the best indications that we have about the effectiveness of this system, at least in terms of firing at large ship targets, basically enemy battleships, both occurred in the same month, November 1942, less than 10 days apart. In Operation Torch at Casablanca, the USS Massachusetts scored a hit on a French super destroyer that maybe because we're still looking for the best indication and the best evidence. The longest hit ever recorded on a moving vessel from another moving vessel with a gun. And this is reported to have been over 28,000 yards, but we're looking for information in the ship's records to see if we can't confirm and prove that. If that's not the longest, we may have to concede to the Warspite or to the Scharnhorst or Gneisenau for that one. But let's hope that the Massachusetts does it. USS Massachusetts also hit the stationary French battleship Jean Bart at about 25,000 yards, and she hit her 5 times, and that silenced and partially sunk the Jean Bart. The hit in the secondary battery magazine of the Jean Bart, which fortunately for the Jean Bart was empty, might very well have sunk or crippled the Jean Bart had that magazine been filled. As it turned out, one of the hits did manage to penetrate all the way through 150 millimeter armor deck, blow up in the ship's rudder post and rudder stock, and disable the rudder, and also caused flooding by the stern, which caused the ship to ground. However, Casablanca Harbor was very shallow, so the ship only sank a few feet by the stern. These results occurred even though the USS Massachusetts had to use the indicator rather than the preferred automatic mode of fire control because her receiver regulators had not been fitted. She was rushed to be the flagship of Operation Torch, and those receiver regulators were only fitted later. Also, her radar in that situation was the earlier Mark III radar, which only gave accurate results in range, and even those results were not nearly as accurate as later main battery fire control radars. The Mark III radar could not accurately control fire in bearing, and also the Jean Bart was adjacent to a pier with multiple other ships there, and therefore did not give a very distinct radar return. In other words, not a sharp blip. So she was not a great radar target for either ranging or full radar fire control. So most of the control, all of the control in train was really done optically, and some of the ranging control was actually done optically as well. In the second example, in the second naval battle of Guadalcanal, USS Washington, equipped with the same Mark 38 director, the same Mark 8 rangekeeper, Mark 41 stable vertical instead of the Mark 43 in the Massachusetts, and Mark III radar, hit the Japanese battleship Kirishima at night at an average range of about 8,500 yards with 20 or more 16-inch shells out of approximately 75 that were fired. That's a 27% hit rate. And if you see the hit rates that occurred in battles like Jutland or pretty much any other surface engagement between battleships, 27% is a phenomenal hit rate. Now, if you read many books, they say that 9 out of 75 shells only hit Jean Bart. But the larger number of hits was actually confirmed by Robert Ballard's exploration and photos of the Kirishima, and a gentleman by the name of Robert Lundgren did a very careful analysis of all of the ship's logs, position reports, etc. And also there was a gentleman who met the Kirishima's actual damage control officer before he passed away, and he knew far more about the damage that the ship had suffered rather than the original report of 9 of 75, which was given by a non-damage control specialist. Now, you may say, well, 8,500 yards, boy, that's close range for a battleship. However, if you remember that the two ships, those two cars on the road, when they were going parallel to each other, is the easiest situation. In this case, the Kirishima was steaming at about 27 knots on an almost reciprocal course from the Washington that was steaming at 26 knots. That's a combined relative speed of about 53 knots, or approximately 60 miles an hour. So the ships are going like this. That is a situation with very rapid changes in the rate of bearing and the rate of range change. Many other fire control systems could not cope with that kind of very, very rapid change, but the Mark 38 director, Mark 8 computer, stable vertical, did the job. Now, interestingly enough, this system has also provided the ability to do a number of other things with similar types of problems. We don't have battleship versus battleship gunfire control problems anymore, but the systems that were utilized in solving the naval fire control problem found applications in other military and non-military situations. For example, the stabilization and fire control system of the gun in the M1 Abrams tank has a system that's basically based on the same principles as this naval fire control system that was designed in the late 1930s. And the one in the Abrams, as I understand, works very, very well, just like the one in the battleship works very, very well. Another example in a non-military application was in the moon landing. Now, in order to get the lunar lander out of lunar orbit down to the moon, the retro rockets had to be fired at exactly the right spot. First to insert it into orbit, and then to get it out of orbit down to the surface of the moon. They also had to be fired for exactly the right amount of time. And this is being done from a moving platform. Now, the calculations that are involved in this are basically exactly the same calculations that are involved in a naval fire control problem. To a target spot from a moving target, trying to hit that. However, in the 1960s, a computer like this was way too heavy and way too big to fit in a spacecraft. So the computation had to be done remotely. That meant the information on the position of the lunar lander, which was done by reference to a fixed reference, a star, had to be transmitted down to Houston. The computations done and then sent back by radio to the lunar landing and then applied in order to fire those retro rockets at exactly the right spot for exactly the right time. And as we all know, the moon landing was successful. Had we not been able to figure out how to solve the naval fire control problem, I don't think we'd have been able to figure out how to solve that problem, because mathematically it's basically the same problem. What are sources that you could get more information about naval fire control? One thing is through videos, and I would recommend ones by Trek NFL. I would recommend the Inside the History videos on naval fire control that's on the Battleship Code website. There are also U.S. Navy training films that are incredibly good in explaining this information in a form that's readily understandable. They are a brilliant example of teaching. Among those are main battery fire control procedures and basic mechanisms of fire control computers. And that's in two parts, 1 and 2. There are also a number of books. Probably the best one, and the one that I rely on most, is Naval Firepower by Norman Friedman, which gives you the history and development of these systems, and also a great deal of information about both the U.S. and other nations' systems, so that you can compare them in what they're able to do. There's also a very, very good website, the Gene Slover U.S. Navy site, which has many of the ordnance publications on these systems and the actual material. And it also has training and operating manuals for these systems. Very, very excellent and very informative system. Lastly, if you'd like to see this for yourself, I would recommend you coming to a memorial ship. The New Jersey, the Massachusetts, the USS Salem, or any of the preserved U.S. Navy battleships will show you these systems. The Texas will have a much earlier and more primitive system. All the fast battleships all have basically the same systems.
Awesome. Thank you very much.
Oh, you're welcome.
Let's have a bit more of a look at these bits of machinery.
Yes.
That's it for this video. Thanks for watching. If you have a comment or suggestion for a ship to review, let us know in the comments below. Don't forget to comment on the pinned post for dry dock questions.